In this video, we're going to be looking at how curves behave and how to find specific points on those curves. Let's begin by looking at a sketch of a curve. Now there we've got a curve. There are some noticeable things about it. First of all, here the curve turns. And if we draw a tangent to the curve, it's level parallel to the x-axis. Here, I've exaggerated it a little bit. The curve is flat and the tangent is again parallel to the x-axis. Here, the curve turns and again a tangent is parallel to the x-axis. Now, one of the things that we do know is that the gradient of a curve is given by dy by dx. And what's clear is that each of these points, here, here, and here, because the tangent is flat, parallel to the x-axis, the gradient is 0, and so dy by dx is 0. Now, for points like these, where dy by dx is 0, we have a special name. We call them stationary points. If you like, the curve sort of isn't moving, it isn't changing at that point. Dy by dx, which is the rate of change, is 0. Now, two of these, I described the curve as turning. I said there the curve was turning, and here again the curve is turning. So that's going from coming up to going down, and this one is from going down to coming up. This one isn't. This one's very different. So these two are special types of stationary points. These two are called turning points. And so at turning points, dy by dx is 0. The thing to realise, though, is that if dy by dx is 0, that doesn't mean we've got a turning point. We might have one of these. That's what makes life just a little bit tricky. But nevertheless, the thing to remember is that turning points, dy by dx is 0. Now let's have a look at the nature of this particular turning point. In the immediate area of it, the curve has no bigger value. We go up, we reach a value, and then we go down again. So this point is called a local maximum, because in the immediate vicinity there is no bigger value. Now usually we forget about the local and we just call it a maximum. Similarly, this point is called a local minimum, because again in this particular region of it the curve goes no lower. So this is the least value in this area, a local minimum. Again, we forget the word local quite often and just use minimum. In essence, this video is going to be about finding these points, maxima and minima, finding these 2 points, maxima and minima, and distinguishing between them, because being able to find them isn't a great deal of use unless we can tell them apart. So we need to be able to distinguish between a maximum and a minimum. So let's begin by exploring what happens around a minimum point. Draw a minimum. Now let's take the tangent at the minimum point. And we know that the gradient of this tangent is 0 because it's parallel to the x-axis. So dy by dx is 0. Let's take a point a little bit before the minimum point and take a tangent at that point, and here we see that the tangent is negative. It's got a negative slope, and so dy by dx is negative. I'm using this as a shorthand for negative. I'm not actually bothered about the value of dy by dx, just its sign. Let's take a point here a little bit after. What's happened there? Well, we can see we've got a line that's got a positive slope to it, which means that dy by dx has got to be positive. So, what's happening as we pass through this point? As x increases, what's happening to dy by dx? Well, as x increases, dy by dx goes from negative to 0 to positive. So dy by dx is increasing as x increases. So let's write that down. Dy by dx is increasing as x increases. What does that mean? Dy by dx is increasing. Well, that means that the rate of change of dy by dx is positive. i.e. d2y by dx squared is greater than 0. So, if d2y by dx squared is greater than 0 and dy by dx is equal to 0, we know that we have got a minimum point. Is that true for all minimum points? Little trick of logic here. Let's just write down what we've got. If dy by dx equals 0 and d2y by dx squared is greater than 0, positive, then we have a minimum. But does it work the other way round? If we have a minimum, do these two both apply? Well, certainly that one does, that if we have a minimum, dy by dx will be 0, but not necessarily this one. Let's have a look at the curve y equals x to the 4th. If I sketch this curve, it looks like that. Here we've clearly got our turning point, our minimum point. Let's have a look what's happening. dy by dx equals, well, y was x to the 4th, so dy by dx is 4x cubed. And we know that for our stationary points, we put it equal to 0, which tells us x equals 0, and x equals 0 tells us that y equals 0. So we know that this is a stationary point. What kind of stationary point is it? Let's do our second derivative. d2y by dx squared is 12x squared, but it equals 0 when x equals 0. So this doesn't work in reverse. If dy by dx is 0 and d2y by dx squared is greater than 0, then we know we have a minimum. But it doesn't work going the other way. What that means is that we have to be especially careful whenever d2y by dx squared comes out to be 0 when we're doing the test, so to speak. We need to look at it in a slightly different way. In fact, what we need to do is go back to basics, and I'll show you an example later where we do go back to basics and how that works out. So, having had a look at a minimum point and looked at it in some detail, let's now move on and look at a maximum point and see what happens there. So here's our maximum point, and at the point itself we know that the tangent is parallel to the x-axis, and so its gradient, and hence dy by dx, is 0. Let's take a point a little bit before that, say there. We can see that we've got a line which has a positive slope to it, and so dy by dx is positive there. And now let's take somewhere just past the point, and if we have a look at this, we can see we've got a tangent where the slope is negative, and so dy by dx is negative. So what's happening as we pass through this maximum point? As x is increasing, what's happening to dy by dx? Well, dy by dx goes from being positive to being 0 to being negative. So as x increases, dy by dx decreases. So as x increases, dy by dx decreases. What does that mean? Well, it must mean that the rate of change of dy by dx is negative as x increases, as we go through this point. At this point, and the derivative of dy by dx is negative. In other words, d2y by dx squared is negative. So let's just write down again what we've got. If dy by dx equals 0 and d2y by dx squared is less than 0, then we have a maximum point. And again, just the same argument applies. Does it work back the same way? Answer, no, it doesn't. And the problem is, what do we do about d2y by dx squared being 0? Well, as I said, we'll show a way of dealing with that in a moment. It's time now to actually look at an example or two and see if we can make use of this test in order to sort out the turning points on a curve. So the first example we're going to have a look at is y equals x cubed minus 3x plus 2. So the first thing we need to do is differentiate it. dy by dx equals, and if we differentiate this, we have 3x squared. We multiply by the index and subtract 1 from it, minus, and the derivative of the 3x is just 3, and this is equal to 0 for stationary points. We can factorise this. There's a common factor of 3, leaves us with x squared minus 1, and this is now recognisable as the difference of two squares. So it factorises as 3 times x minus 1, x plus 1. And that's equal to 0. And now what we can see is that either this bracket is 0 or this bracket is 0, or they're both 0. So we have x equals 1 or x equals minus 1. Now this has just given us the x coordinates of the points that we're interested in. What we need now are the y coordinates, and so let's work those out. X equals 1, y equals, and we'll substitute it in on the very first line. So that's 1 cubed is just 1, minus 3 times by 1 is minus 3, plus 2. So altogether that gives us 0. And so our point, our stationary point, is 1, 0. If we take x equals minus 1, then y is equal to, and we put minus 1 in there, well, minus 1 cubed is just minus 1. Minus 3 times by minus 1 is plus 3, and plus 2 at the end, and altogether 3 plus 2 is 5, take away 1 is 4. And so our other stationary point is minus 1, 4. And now we need to decide, are these points maxima, minima, or that funny one where it was flat? So in order to sort that out, what we need to have a look at is the second derivative. So I'm going to write the equation of the curve down again, and then I'm going to write down this first derivative, then the points, and then the second derivative. So with y equals x cubed minus 3x plus 2, we've got the first derivative, dy by dx, 3x squared minus 3, and the points that we're interested in were the points 1, 0, and minus 1, 4. So now let's take the second derivative, d2y by dx squared equals. So we differentiate this, and the derivative of the first term we multiply by the index, so 2 3s are 6, and take 1 off the index, that's x. And the derivative of 3 is just 0. So let's now look at the points, and it's the values of x we're interested in. So x equals 1, d2y by dx squared equals 6. So this is positive. And what do we know? We know that if dy by dx is 0, and if d2y by dx squared is positive, then the point we're looking at is a minimum turning point. So therefore, 1, 0 is a minimum, min for short. X equals minus 1, this is our second point. d2y by dx squared is equal to minus 6, and that is negative. The value of these doesn't matter, it's their sign that matters. And therefore, what do we know? We know that if dy by dx is 0 and d2y by dx squared is negative, then we have got a maximum. So minus 1, 4 is a max. One of the things that this does help us do is when we do know the turning points, we can use this to help us gain a picture of the graph, to help us sketch a picture. So let's just plot these 2 points and see if by plotting them we can build up a picture of the graph. Now this won't be an exact picture. The scales will be different. They'll be a little bit cramped in some cases, expanded in others, because what we're trying to show are the important points on the graph. So we've 1 and minus 1 were our 2 important values of x. And we know that 1, 0 was one of our turning points. And if we just go back, we know that 1, 0 was a minimum turning point. So we know that at this point the curve looks like that. The other point was minus 1, 4, there. And we know that at that point the curve was like that. It was a maximum. The other thing we know is that there are no turning points anywhere else. These are the only ones. And so effectively we can join up the curve and so that we get a rough picture that it looks something like that. We can find this point, of course, by substituting in x equals 0. Remember, our curve was y equals x cubed minus 3x plus 2. And if x is 0, then this must be 2 here. And this we can find by equating y to 0 and solving. But we're not interested in that at the moment. It's the idea of using this maximum and minimum turning points in order to help us gain a picture of the shape of the curve. We're going to have a look at an example now where the method we use is one that enables us to go back to first principles. And this is also the method that we would use if d2y by dx squared turned out to be 0. So it's a very useful method to have at your fingertips. So let's begin. We're going to be looking at finding the turning points of this particular curve. X minus 1 all squared over x. Well, it's a u over a v. It's a quotient. So we need to be able to differentiate as though it were a quotient. So let's remember how we do that. We take the bottom, v, that's x, and we multiply x by the derivative of u, what's on top. So that's 2 times x minus 1 times the derivative of what's inside, a 1. And then minus, and we take u, x minus 1 all squared, and we multiply it by the derivative of v, what's on the bottom. And that's the derivative of x, so that's just 1, and then it's all over x squared. And for our stationary points, we put this equal to 0. Now, let's have a look at this. We need to tidy it up. It looks a bit of a mess. So let's have a look for some common factors. Well, here we've got an x minus 1 and here as well. So let's take that x minus 1 out as a factor. And let's have a look what we're left with. Well, here we've got 2 and x giving us 2x and a 1 times by 1, that's still 2x minus, and here we've got 1 times by, now we just took out x minus 1 as a factor, so it's minus x minus 1. And notice I've kept it in the bracket because it's the whole of x minus 1 that I'm taking away. And close that bracket and all over x squared. So this is still dy by dx. Now I can simplify what's in the bracket and have dy by dx is equal to x minus 1 times by, now I have 2x take away x, that's just an x, but then I've also to take away minus 1, and so that gives me plus 1. All over x squared, and this is to be equal to 0 for my stationary points. Now, when we have an expression like that that's equal to 0, it's only the numerator that we're interested in. It's only the numerator that will make this expression 0. So, what we've got is x minus 1, x plus 1 equals 0. And that tells us that either this bracket is equal to 0 or that bracket is equal to 0. In other words, x minus 1 equals 0 or x plus 1 equals 0. So x equals 1 or x equals minus 1. Now it's the points we're after, so let's now calculate the values of y, remembering that y is equal to x minus 1 all squared all over x. So let's take x equals 1 and see what that gives us for y. We put 1 in there, we have 1 minus 1 all squared over 1. Well, that's just 0, because 1 minus 1 is 0. Square it, that's still 0. Divide by 1, the answer is still 0. So one of our points is 1, 0. That's one of our stationary points. Now let's do x equals minus 1. And y is equal to minus 1 minus 1 all squared all over minus 1. Minus 1 is minus 2, and we square it, so that's 4, but we divide by minus 1, so that is minus 4. So our other point is minus 1 minus 4. So we've got 2 points, which are stationary points, and we need to find out, are they turning points? And if they are turning points, are they maxima or minima? So let's write down again y, dy by dx, and our points. So we had y, that was x minus 1 all squared over x. And we had dy by dx, and dy by dx was over x squared. And let's just go back so we can see what the numerator was. It was x minus 1 times by x plus 1. X minus 1 times by x plus 1. And our 2 points are the points 1, 0, and minus 1, minus 4. Now, in order to sort out if these are turning points, and if they are, which is a maximum and which is a minimum, then we need to differentiate this again. And that is very, very fearsome. Very fearsome indeed. Is it really worth differentiating it again? We might make a mistake. The algebra might go wrong. So, rather than differentiating it again, let's do what we did before. Let's look at the gradient a little bit before x equals 1, at x equals 1, and a little bit after x equals 1, and form a picture from doing that of whether this is a maximum or a minimum point. And this method that we're going to have a look at also works when d2y by dx squared is 0. So hence it's a good method, and it's well worth adding it to your armoury of techniques for looking at stationary points. So let's set this up. And the way we're going to set it up is to have a little table. So here's dy by dx, and here is the point we're interested in at x equals 1. Now I want to look a little bit before x equals 1. So I'm going to say this is x equals 1 minus epsilon. And all I mean by epsilon is a little positive bit of x. 0.1, 0.01 if you like. And I'm also going to look at the gradient a little bit after x equals 1, so let me call that 1 plus epsilon. Now, I'm not interested in the value of dy by dx, I'm only interested in its sign, whether it's positive or negative. I know that when x equals 1, dy by dx is 0. what happens if I am a little bit before x equals 1? X is a little bit less than 1. So I've something a little bit less than 1, and I'm taking 1 away. So the answer to that is negative. This bracket here is negative. However, I've got something that's a little bit less than 1 plus 1, that's positive. So I have a negative times by a positive, and I've got x squared on the bottom here, and x squared is positive. So a negative times a positive divided by a positive is a negative. Let's have a look when x is a little bit more than 1, a little bit bigger than 1, 1.01. Well, 1 take away 1, well, a little bit more than 1 we say take away 1, that's positive. 1 plus a little bit more than 1, that's positive again. And this is definitely positive in the denominator. So with a positive times by a positive divided by a positive gives us a positive. So if we sketch the slopes of the tangents, we have a negative slope, a flat slope, and a positive slope. And so what we can see is that this defines the shape of a minimum. And so we can conclude that 1, 0 is a minimum point. And notice what we've done is go back to basics. This is how we arrived at our test for d2y by dx squared. Now let's do it again for this point, -1, -4. So we've got dy by dx is equal to x minus 1 times by x plus 1 all over x squared. And the point we're having a look at is -1 minus 4. So let's set up our table again. We're looking at the sign of dy by dx. And we're looking at it at the point x equals -1 as we pass through that point as x increases. So we want to know what's happening a little bit before that, -1 minus epsilon. And we want to know what's happening a little bit after that, -1 plus epsilon. Well, we know that when x is -1, dy by dx is 0, because this factor here is 0. What happens if x is a little bit less than -1? Something like -1.1. Well, we've got -1.1 take away 1. That's definitely negative. -1.1 add on 1, that's -0.1. That's definitely negative as well. However, on the bottom here, we've got a number and we're squaring it, so it must be positive. So we have a negative times a negative, which is a positive, divided by a positive. So the answer must be positive. Now let's have a look a little bit after x equals -1. -1 plus a little bit. So the little bit might be 0.1, and -1 plus a little bit would then be -0.9. So we've got -0.9 minus 1. Well, that's -1.9. It's negative. I've got -0.9 plus 1. Well, that's 0.1. It's positive. So I have a negative times a positive, and this term, x squared, is always positive because it's a square. So we've got a negative times by a positive and divided by a positive, so our answer must be negative. So let's sketch the shape. We've got a positive slope, a flat slope, a negative slope. And this defines the shape of a maximum. And so we can say -1 minus 4 is a maximum. Finally, let's just see how this helps us to sketch the curve. We recall the equation of the curve, y equals x minus 1 all squared over x, and we had a maximum point at minus 1, 4, and we had a minimum point at 1, 0. So some axes. Let's mark the point 1 and the point minus 1, those on the x-axis. Now 1, 0 is here, and we know it's a minimum, so we know it looks something like that there. Minus 1, minus 4, down here somewhere, and we know that that's a maximum, so it kind of looks like that. How can we join these up? Well, clearly there's something odd going on around 0 here, because the curve seems to go that way and that way. It seems to go in opposite directions. What's happening here? What's going on? Well, let's just have a little think about this. As x approaches 0 from above, then this is always going to be positive, but this is going to be positive as well, and we're dividing by something very, very small. Our answer is going to be very, very big. So we're going to have something up there. When x is negative but near to 0, this is still going to be positive because we're squaring it, but we're dividing it by something which is getting very, very small but negative. So the answer is going to be very big but negative, and so it will be somewhere down here. So what we can see is that the curve is going to look something like that. And there will in fact be this almost what looks like a sort of hole in the middle of it, bang on this value, x equals 0. So what have we done? We have found out how to find stationary points. Stationary points occur on a curve when dy by dx is 0. If dy by dx is 0, then some of those points are what we call turning points, maxima or minima. And we can find those in one of two ways. If dy by dx is 0 and d2y by dx squared is greater than 0, then we know for sure that we have got a minimum point. If dy by dx is 0 and d2y by dx squared is negative, then we know for sure we've got a maximum point. If, however, d2y by dx squared is 0, then we have no information whatsoever. And we need to look very closely, using the methods that I've just shown here, in order to determine what kind of stationary point we've got. Whether we've got a maximum, whether we've got a minimum, or whether we've got one of those odd ones that looked a little bit flat, a kink in the curve.